Congratulations, you made to lecture 11, and it's the final lecture of the entire semester. Density measures how much mass an object occupies. You can refer to this as the lightness or heaviness of materials of the same size. In the GIF, Squidward is floating because ice is less dense than water. However, it's important to remember that density is a physical property of matter and is measured by dividing the mass by the volume, or in the case of weight density, dividing weight by the volume. Okay, let's do an example. So how dense is snow? So we know the equation for density is mass divided by volume. Right, to calculate the density of snow, we first need to collect some snow and record the volume. So in this GIF, you notice the volume of the snow we collected is 400 milliliters. Now we're going to let the snow melt and figure out how much water we have. Water is special because 1 milliliter of water is equal to 1 gram of water. And this is simply because the density of water is 1. So now we have 200 grams of snow, or in this case, now water. Okay, now let's solve. Let's plug it in the equation. So we know the mass is 200 grams, the volume is 400 milliliters, and when we divide that, we get 0.5 grams per milliliter, which is the density. Being that we got a density of 0.5 grams per milliliter, this tells us that snow is less dense than water. Here's an example for you to do on your own. Calculate the density of the fresh snow, and then calculate the density of the settled snow. The answer is on this slide, but you'll notice that the density is different. Spend some time comparing and contrasting fresh snow and settled snow. Which one would be more dense, which one is less dense, and why? When we think of fluids, we often think of liquids, but solids, liquids, and gases are all fluid because they're in motion. This brings us to our next topic, pressure. Pressure is the force per unit area that one object exerts on another. Force is typically measured in units of pounds per feet squared, newtons per meter squared, or pascals. Spend some time analyzing the illustration. How does the illustration demonstrate the pressure equation? Water pressure is pressure in liquids. Pressure in liquids is dependent on depth, not volume. In the first photo, the force arrows illustrate the forces of pressure. Pressure acts equally in all directions and acts perpendicular to surfaces. I'm going to give you 3 examples. Try and envision these examples in your head or draw them out. Number 1, your ears feel the same amount of pressure underwater no matter how you tip your head. Number 2, the bottom of a boat is pushed upward by water pressure. And number 3, pressure acts upward when pushing a beach ball underwater. Water pressure is independent of the shape of the container. Whatever the shape of the container, pressure at any particular depth is the same. This translates into the equation liquid pressure equals weight density times depth. In the second photo, you'll notice the water exits the holes in the container at a 90-degree angle, or perpendicular to the surface before curving downward due to gravity. The only difference between the holes is the depth. Make sure you note how this is related to exiting speed. I couldn't find a water tower at Bikini Bottom. If anyone knows of a photo like that, please email it to me. All right, so in almost every town or city, you'll find a water tower. The force of gravity acting on the water in a tall tower produces pressure in underground pipes that supply many homes with reliable water pressure. So, if everyone in your town is experiencing low water pressure, there may be an issue with your water tower. When SpongeBob gets in the tub, SpongeBob will feel lighter. This apparent loss of weight is called buoyancy, and it equals the weight of the water displaced. In the GIF, the water displaced is the water that splashes out the tub. Archimedes' principle relates buoyancy to displaced liquid. It states that an immersed body, completely or partially, experiences a buoyancy force that is equal to the weight of the liquid it displaces. This applies to both gases and liquids. For example, if a 5 kilogram block is submerged in water and apparently weighs 2 kilograms, then the buoyancy force or weight of the water displaced is 3 kilograms. In this example, apparently refers to when the block is submerged. This is called the displacement rule. In the displacement rule, a completely submerged object always displaces a volume of liquid equal to its own volume. So, in summary, buoyant force is equal to the weight of the fluid displaced, but is also to be understood as pressure differences. All right, so this is the last thing we're going to talk about under Archimedes' principle, and it's flotation. So the principle of flotation simply states that a floating object displaces a weight of fluid equal to its own weight. Let's move on to gases. Pressure in gas or gas pressure is a measure of the amount of force per area that a gas exerts against containing walls. Here, the force is exerted by the motion of molecules bouncing around or kinetic energy. And temperature is the measure of kinetic energy per molecules of the gas. To relate pressure to density, we use Boyle's law, which describes the relationship between pressure and volume for ideal gases. An ideal gas is one in which intermolecular forces play no role. In this class, we're only concerned with ideal gases because real gases can be rather complex. Now, this is what you need to underline in your notes. The law states that pressure times volume is constant for a given mass of confined gas, regardless of changes in pressure or volume, as long as temperature is constant. This translates into the equation pressure 1 times volume 1 equals pressure 2 times volume 2. Spend some time looking at the example on the slide. Okay, I lied. This is another slide on Archimedes' principle. Archimedes' principle applies to fluids. Remember, that's liquids and gases alike. Let's look at the example on the slide. The force of air or liquid on the bottom of the bubble in the GIF is greater than the force on the top. It also means net horizontal forces cancel, but not the vertical ones, which supplies the buoyant force. And this buoyant force equals the weight of displaced air. If you need another example, think of a hot air balloon. I chose this one because we all know that the laws of physics on SpongeBob more so align with life on land than they do with life under the sea. The atmosphere exerts pressure on everything around it. For SpongeBob, who lives under the sea, he experiences water pressure, but for us, humans living on Earth, we experience atmospheric pressure. Atmospheric pressure is caused by the weight of air. It varies from one locality to another because it's not uniform, but these measurements are used to predict weather conditions. While some of us may live in the mountains, we typically use the sea level constant. At sea level, atmospheric pressure is 101 kilopascals. The weight of air pressing down on a 1 meter squared at sea level is approximately 100,000 newtons. So, atmospheric pressure is 10 to the fifth power newtons per meter squared. A mechanical pump is a device that creates a vacuum and moves fluids by mechanical action to be converted into energy. The way it works is like this. When the piston is lifted, the intake valve opens and air moves in to fill the empty space. When the piston is moved downward, the outlet valve opens and the air is pushed out. The highest the atmosphere can push water into a vacuum or mechanical pump is 10.3 meters because the pressure at the bottom of a column of air reaching to the top of the atmosphere is the same as the pressure at the bottom of a column of water 10.3 meters high. However, if a mechanical pump does not depend on atmospheric pressure, it does not have a 10.3 meter limit. Now let's take a break from these slides and watch a very informative video about barometers and their history. If you are watching on YouTube, the link is in the description box. Pascal's principle states that a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. This applies to all fluids, gases, and liquids. Now, in the photo on the slide, as the person squeezes on the bulb, the liquid is evenly distributed, which is why all the valves have the same height. Bernoulli's principle states that where the speed of a fluid increases, internal pressure in the fluid decreases. This is typically applied when we're talking about a smooth, steady flow. In fluid flow diagrams, thin lines represent the fluid's motion. Thinner lines mean the flow speed is greater and pressure within the fluid is less. Note the larger bubbles. Wider lines mean the flow speed is less and the pressure within the fluid is greater. Greater pressure squeezes bubbles smaller. Both of these diagrams illustrate continuous flow. For continuous flow, the volume of the fluid flowing past any cross-section of a pipe in a given time is the same as the fluid flowing past any other section of the pipe, even if the pipe widens or narrows. There are two other types of fluid flow you need to consider. Laminar flow, which is smooth, steady flow of constant density fluid, and turbulent flow, which is when flow speed above a critical point becomes chaotic. If you've ever flown on a plane, you have probably experienced both of these flow types. Here's an application of Bernoulli's principle. Moving air gains speed above the roof of a house. This change in air velocity means reduced pressure on the roof. Therefore, air pressure inside the house is greater, which can raise the roof. Sounds like a hurricane to me. I've always found this episode of SpongeBob hilarious, where they're flying planes under the sea, but the ocean and air are both fluids, so I guess it could work in theory, but instead we're going to talk about the airplane wing on this slide. So in the drawing on the right, the vertical vector represents the net upward force, which is lift, that results from more air pressure below the wing than above the wing. The horizontal vector represents the air drag force. This is what makes an airplane aerodynamic. So now, relate this back to drag force that was mentioned in Lecture 10. In SpongeBob, the boats are more like cars than boats. But when the speed of water increases between boats, Bernoulli must be compensated for, or else the boats will collide. That's it for Lecture 11.